So now in our next section, this is where we're going to start to get into more of the details of the layer 2 switching, where the first goal of the layer 2 network is always going to be to get basic connectivity between devices that are in the same IP subnets, which means that they're generally going to be in the same broadcast domains. Once we have connectivity on the LAN, then we can deal with any of the layer 3 protocols, like our EIGRP routing or OSPF routing, BGP routing. But unless we can get the devices to talk directly connected on the LAN, then any of the other stuff is not going to work, like at the actual application layer. First thing that's going to come along with this in switching is the VLAN design, or the virtual local area networks, where the idea behind this is that the hosts in the same virtual LAN are going to share the same broadcast domain, where essentially now the switch is going to have different copies of the CAM table or different copies of the MAC address table depending on what the VLAN assignment is. So if we were to have a case where there were 2 hosts in VLAN 10, when the switch hears a frame that is coming in from router 1, let's say that this is our IP version 4 address resolution protocol request, or our ARP request, where router 1 is trying to send a packet to router 3. Maybe it's trying to send a ping. But before it does this, router 1 knows that there has to be an association at layer 3 with our IP packet to layer 2 with our MAC address over Ethernet. So this is what our ARP packet is designed to do, is tell router 1 that if I'm trying to send an IP packet to this address, what is the MAC address that corresponds to this? Now inside of the actual ARP request, router 1 is going to set the IP source address to itself, which in this case would be 10.0.0.1. The IP destination is whoever I'm trying to reach. So on router 3 we would have 10.0.0.3. The layer 2 MAC address source is going to be whatever router 1's MAC address is. But the layer 2 MAC address destination, router 1 doesn't know this. This is what it's trying to figure out. So it sets this address to be the all Fs, where the idea is that we're going to get the layer 2 network, or essentially the Ethernet switches, to send the packet everywhere, and hopefully it's eventually going to get to router 3, which I'm trying to reach. So when the switch does this, it's going to look at, first off, what is the source address that the layer 2 packet came from, where the layer 2 source was router 1's MAC address. From the switch's perspective, it says this frame came in on fast Ethernet 0/1. So now I know that a couple things are true about the network. I now know that on port FA0/1 that the MAC address of whatever router 1's MAC address exists. Basically, I now know what's the location of router 1 in the network. But it doesn't yet know where is router 3 located. So it looks at the layer 2 destination. It says this is the all Fs address. This is the broadcast address. Now, if these 2 ports are in the same VLAN, it means that they're in the same broadcast domain. So this layer 2 destination of all Fs, it's going to go out all ports except the one that it came in on. So switch 1 sends the frame this way. This again is what we consider our flooding, where I'm trying to build the MAC address table, but to do this I have to send the packets everywhere and then try to solicit a response to come back in. So the idea behind this is twofold. Router 1 is trying to figure out what is router 3's MAC address, and the switch in the middle is trying to figure out what are the MAC addresses of the end hosts. So router 3 gets this. It says the IP destination address is me. Destination is 10.0.0.3. This is router 1, which is 10.0.0.1. It's 10.0.0.1 asking me what is my MAC address. Based on this, router 3 also knows now what is the MAC address of router 1. So it can populate in its own ARP cache. Basically, what is the relationship between those 2 addresses? So I now know that the IP address 10.0.0.1 maps to this MAC address, whatever router 1 requested it from. But now router 3 is going to send the ARP reply, where the ARP reply is going to come from its own layer 3 address. So it's coming from 10.0.0.3 at IP. It's going to router 1. The layer 3 destination is 10.0.0.1. The layer 2 source address is now the MAC address of router 3's interface. And the layer 2 MAC address destination is going to be what router 1's was. But the key is that once this packet is received back in from the switch now knows that on fast Ethernet 0/3, that router 3's MAC address is located there. So from here on out, any layer 2 frames that are moving between router 1 and router 3, I can look at the MAC address table and now I know where to send them. So I don't need to simply flood them to every single port in the network. I have this mapping table that's going to allow me to switch my traffic. And this is the main idea of the VLAN, that the ports that are in the same VLAN are going to be in the same broadcast domain, which is going to allow the switch to figure out what are the MAC addresses that exist in that virtual network. This also means that traffic inside the VLAN is going to use that layer 2 switching table or the CAM table for its decisions. So traffic in the VLAN is switched, but traffic between VLANs has to be routed, because when an ARP request is generated in VLAN 10, it can't be forwarded to VLAN 20 because they have separate MAC address tables or separate CAM tables. The big advantage of this is that we can now build the network based on a logical separation and not necessarily on a physical separation, where I could have 2 hosts that are in the same VLAN that are spanning between multiple switches, as long as the different layer 2 devices agree on what the VLAN numbers are. And the way that we do this is with what's known as a VLAN trunk, or simply a trunk. These are going to be the ports that are between the switches that carry the multiple VLAN numbers, which means that we can essentially span the MAC address table between multiple physical switches. Right. Okay, so the question is, if you had a Cisco switch here and you had some other vendor, let's say you have like a Netgear switch, and I'm trying to get a host in VLAN 10 to talk to a host in VLAN 10 down here. The key is that when the frame comes in from the originating host, let's say router 2 is trying to send a ping to router 1. Router 2 is going to say that the IP source address is its IP, let's say 10.0.0.2. The IP destination is router 1, 10.0.0.1. The MAC address source, which is the layer 2 header, that's going to be router 2's MAC address. The MAC address destination is going to be router 1's MAC address. Because we're assuming that they already knew this based on the ARP request and reply. When the switch receives this frame, it says it came in on this port fast Ethernet 0/2, whose VLAN membership is 10. It would already know that the MAC address of router 1 is located on this port. So in the MAC address table, or in the CAM table, is going to have these multiple port entries and the MAC address entries. And we're going to look at this on the command line a little bit, so it'll make a little bit more sense. But the next thing is that when the Ethernet frame is sent between the switches, we need some way to encode this value. And this is what the trunk is allowing us to do. That on the trunk link, we can run a protocol that is known as .1q or 802.1q, which is a standard protocol specification that says how are you supposed to include the VLAN number when you send the frames between the switches. So based on the fact that the Cisco switch and the Netgear switch both agree on this Ethernet standard, the VLAN can span between multiple physical devices. If on the Cisco switch we were to run the proprietary version, which is ISL, then it would not work. But only because they can encode the VLAN number on the trunk link between them, then it's going to be valid.
Another question is, so we're working with a service provider, and we have some interfaces on the MPLS router, but the VLAN call VLAN 1, 2, 3, 4, 5.
Right.
But we call it 6, 7, 8, 9, 10. But 1 is actually our 6, 2 is actually our 7.
You can do that, but the problem is that inside, it depends on if you're running spanning tree or not. And we'll talk about that when we get into spanning tree in more detail. When I send you a spanning tree advertisement, which is known as a bridge protocol data unit or a BPDU, when I send you the advertisement, I'm going to put the VLAN number inside of the header. When you receive that, if it doesn't match your number, you usually throw it away because it's normally an indication of a loop in spanning tree. But if they're going over MPLS, it could be a different case because there's a kind of interoperability where you take the original header and you don't look inside of it. You just bridge it across the IP network. But that's a good question. We'll come back to that when we talk about spanning tree. So a couple key points here, that the switches that are in the same VLAN, or excuse me, not the switches, the hosts that are in the same VLAN, they're sharing the same copy of the CAM table or the same copy of the MAC address table. And this is how the switch is going to move the traffic between them. If we want to span between multiple physical switches, then we just need some way to carry this traffic across the links between the switches. This is what the trunks are going to do for us. Now, you may have seen that in some older documents or some previous recommendation about this, that previously the VLAN a lot of times was related to the role in the network. Like maybe you had one VLAN that is for accounting, one VLAN that is for sales. In today's networks, most of the time the VLAN is going to be directly related to the physical location, where on one of your access switches, maybe you have VLAN 10, on a different access switch you have VLAN 20, and they're unrelated. The reason why is that originally the idea was that 80% of your network traffic was inside of the same VLAN, and 20% of the traffic went to another VLAN, or it went to the WAN, where in today's networks, in most cases, it's actually the opposite of this, where 20% of your traffic is local, and 80% of your traffic is remote. So it's typically a simpler design just to match the physical geography of the network to the VLANs now. And this will make a little bit more sense when we start to talk about spanning tree and some of the advantages of the new version of spanning tree versus the old one, versus the common spanning tree and the per VLAN spanning tree, and why you would want to limit the size of the broadcast domain and the size of the spanning tree domain as much as possible. Now, the VLAN itself is a 12-bit field, which means the VLAN number could be somewhere from 0 to 4094. Values 0 and 4095, these are reserved. So the actual VLAN number is going to be somewhere from 1 to 4094, where there's a couple of normal VLAN ranges and then an extended VLAN range. The normal VLAN range goes from 1 to 1005. The first one is dedicated for your default Ethernet VLAN. So this is where all the ports are going to be on the switch by default. The other four, 1002 and 1004, and 1003 and 1005, these are for backward support of the legacy protocols FDDI and Token Ring, where these were the IBM standard LAN protocols, where Token Ring was a 16 megabit per second ring over copper. FDDI was a 100 megabit per second ring over fiber. But in today's networks, these are rarely used anymore. We're dealing with just Ethernet, so these numbers aren't going to be used for anything. But you will see that they are going to be assigned automatically on the switches. So if we were to go to the Catalyst command line and look at the show VLAN, we would see that these numbers are always going to be reserved, where all of the ports are going to be in the default Ethernet VLAN, where in this case, this is everything that goes from Fast Ethernet 1 to 24, then a couple of these uplinks here. And then there's the FDDI default, the FDDI net, the Token Ring, and the Token Ring net. These ones are going to be unused, so you can just ignore them. But the key is that you can't use these numbers for assignment. The valid range for assignment then is going to be from 1 to 1001 for the normal VLAN range. Then above this, we have what's known as the new extended VLAN range, which is 1006 to 4094. And we'll talk about this more later when we get to private VLANs, and then when we also get to transparent VTP mode. So typically your VLAN number is going to be somewhere from 1 to 1001. Now again, the reason that this is going to be important is that the copy of the MAC address table is directly related to the VLAN number. So if I'm in VLAN 2 and somebody else is in VLAN 2, it means that we're using the same copy of the CAM table on the switches in order to get traffic between us. So traffic inside the VLAN is layer 2 switched. Traffic between VLANs needs to be layer 3 routed, because we need to change the layer 2 protocol header. The actual creation of the VLANs is going to work two different ways on the switches. Normally, by default, when you create the VLAN on the switch, it's not going to store it in its normal running configuration like other changes you make. Like if I were to assign an IP address or create an access list or do some routing protocol config, normally I would see this on the switch or the router by looking at the show run or the write terminal, where this is going to show me the configuration changes. For the VLANs, this is stored in a file on flash that is the VLAN database, or the VLAN.dat. And you can see this if you look at the dir for a directory output, that normally there would be a VLAN.dat file here. If I were to make a change to a VLAN, let's say I create VLAN 2, once I do this, the switch is going to create that file that is VLAN.dat right there. The problem with this is that it's a binary file, so you can't actually read what's inside of it. If we were to say more /:VLAN.dat, you can see that VLAN 2 is listed in there, but it's a binary encoding, so you can't really read the file. The reason that this is important to know is that when you're making backups of the configurations of your network devices, normally you need to save the running config, but in the case of the switches, you also need to back up the VLAN.dat file. So if you had some sort of management software that's going in and like downloading your configurations through TFTP or downloading them through SNMP, you need to make sure to include that file, the VLAN.dat.
When you store the configuration file on your core, you actually transfer the VLAN.dat first before the configuration file, or? So I know the VLAN.dat actually maintain all the VLAN information.
The VLAN numbers, right.
Right. So when you do a restore, you actually restore VLAN.dat first, or?
It wouldn't really matter the order, as long as it's in there. Question?
It used to be you could manipulate the database directly, or is Cisco iOS completely moving away from that?
There is a way that you can do it in some platforms. So we'll look at that actually next. There's two ways you can change it. There's an exec mode VLAN database, and there's a global configuration mode. Some of the old platforms require you to do it in the VLAN database mode. So from exec mode, which is the switch's host name followed by the #, if you say VLAN database, it says it's recommended to configure the VLANs in config mode. This is being deprecated. Basically means in a later software version, they're not going to give you this option anymore. So you can still do it, it's fine. If you make a change like VLAN 3, VLAN 4, VLAN 5, this is creating different MAC address tables. So now I have separate tables, one that's for VLAN 3, one that's for VLAN 4, one that's for VLAN 5. Once I'm done with this in the database, I would need to say apply and then exit. The difference between doing this in a global configuration is that you don't need to do the apply. It happens automatically. And you can create and edit multiple VLANs at a time. So in global configuration, I could say VLAN 10 to 20. I could say VLAN 30, 40, 50, 60. And it just saves me a little time in the administration of it. The end result is going to be the same, though. If I look at the show VLAN, the ones that I created in database mode are there, which are numbers 2 through 5. The ones I created in global configuration, likewise. Question?
If you use BTP, doesn't that guarantee the VLAN data is in sync? Or?
It can. It can. And we're gonna talk about that today. But as a standalone configuration with nothing else changed yet, these values are only locally significant. So this means that if I was trying to get traffic from router 2 to be able to get to router 1, if this port here is in VLAN 10 and this port here is in VLAN 10, I need to make sure that switch 1 and switch 2 have created those numbers first. Because if I don't create the number, it means there's no MAC address table that I can use for flooding. And again, you could see this just by looking at either the show VLAN or the show VLAN brief. There's also some other minor options you can change here. A lot of times you'll put a description for them, which is basically the name, to make it a little bit easier to keep track of what is that VLAN for. Like I could say VLAN 2 has a name of my web servers. VLAN 3 has a name of sales users. So now when I look at the show VLANs, it makes it a little bit more obvious from a documentation point of view. Why am I using this VLAN and what role should it be assigned for? But if you don't put this, it's going to use a default name, which is VLAN and then the number after it. So again, two different ways. You could do it in the database or you could do it in global config. And the advantage of doing it in global config is that you can do multiple creations at the same time. This is saying create 30, 40, 50, 51, 52, 3, 4, 5. To check that this is correct, again, we would either look at the show VLANs, or the show VLAN brief. It's going to show you not only what are the names or numbers, but what are the port assignments, which in this case, VLANs 10, 20, 30, 40, 50, etc. have been created, but there's no ports that are actually using this yet. So it's a two-step process. Create the VLAN, then our next step would be to do the assignment or to do the VLAN membership. So the membership, this is where we're actually telling the port which MAC address table are you going to exist in. By default, all of the ports are going to be in VLAN 1. At the interface level on these Catalyst iOS platforms, there's 3 different types of interfaces or 3 different types of switch ports that we can configure. Where a switch port means that it's going to be used for layer 2 switching. The opposite of this would be no switch port, which we'll see is when we're running the interface in layer 3 mode. It's called a native layer 3 routed interface. If you say no switch port, the interface is going to behave like a normal router interface. That you could put an IP address on it, you could put an access list on it, you could do any other layer 3 options. But by default, the interfaces are going to be switch ports. They're assigned to VLANs, and they're going to be used for switching traffic based on the MAC address table. First of these are going to be the access switch ports. This is where we have just one single VLAN assignment per interface. This would be like where you connect down to your end host or to your printer or whatever is the end client that's connecting to the LAN. The other option would be a trunk port. This is generally the ports that are connecting between the switches that are going to be carrying multiple VLANs at the same time. Some platforms also support what are known as dynamic switch ports, where it can automatically choose between the two of them. It can figure out, am I connected to another switch, and if so, automatically run the interface in trunking mode, or if I'm not connected to a switch, I'm going to default back to access mode. Most of the platforms run this by default, that the interfaces are in dynamic mode. The way that you can check this, though, is to look at the show interfaces switch port. And this is going to show us all of the possible layer 2 options that we would want to know about the interfaces. Where this here is listing all of them, I could be more specific and say something like show interface fast Ethernet 0/1 switch port. And it'll show me just those particular options. So here in this case it says that switch port is enabled. This means the interface is running in layer 2 mode. In layer 2 mode, the port is either going to be an access port, it's going to be a trunk port, or if the negotiation of trunking is on, it could be a dynamic port. Dynamic port. In this case, it says that this interface is configured as dynamic auto mode, where with dynamic mode, it means that the negotiation of trunking is on. I'm going to try to figure out, am I attached to an end host or am I attached to another switch? If I'm attached to another switch, I can automatically form a trunk link and then use that to carry multiple VLANs at the same time. So next, let's look at a basic example of this, where I want to get traffic to move between router 1 and router 3, which means that from the switch's point of view, they have to be in the same VLAN in order for the layer 2 MAC addresses to be exchanged directly between them. So on router 1 and 3, I'm going to do a basic configuration. At this point, there's essentially no configuration on any of the devices. They just boot it up with their blank configs. So the only changes I'm really going to make here are just to put host names and address assignments on the routers. And actually, I forgot to talk about this before, the physical diagram of the network. If you go to members.ind.com and go to that page about the rack access, I'm going to make some additional printouts of these today as well. I forgot to include those with the binders. Under rack rentals, there is a rack access info tab here. This goes over some more details about the logins and stuff like that. But here there's a link to the rack hardware specification and diagram. This is the physical topology that we're going to be using. So it shows you what are the routers, what are their memory and modules and stuff like that. It shows the physical WAN cabling, which we don't need to use right now, but then also the physical LAN cabling. So here it's listed in a diagram, and then the next page it's listed in a table. It's the same as the CCIE racks, yeah. So I'll make some printouts of this later so everyone can follow along what the physical topology looks like. But for this example, they're connected how the diagram shows it. That router 1's fast Ethernet 0/0 is physically cabled to fast Ethernet 0/1 on switch 1. And router 3's fast Ethernet 0/0 is physically cabled to fast Ethernet 0/3 on switch 1. If I wanted to do a basic verification of this, what command can I use on the routers and switches? Would be show CDP neighbors for the Cisco Discovery Protocol. Before I do this, there's a couple minor changes I need to make. I'm going to give the devices host names. So in global config, I'll simply say host name, this is router 3, or R3. On switch 1, the same thing. So in global config, host name is SW1. Then depending on the version of iOS and the platform, if you look at the show IP interface brief, you may find that by default the interfaces are disabled. So I need to take them out of software disabled state or administratively down. So I need to say what at the interface level?
No shut.
No shutdown. So now on the switch, we can see there's some log messages. It says that the physical link for fast Ethernet 0/1, this is up. It means there's no cabling problems. The line protocol is also up. It means that the other side is running Ethernet. So the first one is the layer 1 status. The second one is the layer 2 status. If I now show CDP neighbors, I should see here shortly the connections to router 1 and router 3. What you may also want to do here is put descriptions on the interfaces. It makes it a little bit easier to kind of document the network. That if I were to go to interface fast Ethernet 0/1 and say the description is to R1 FA 0/0, and this other interface goes to router 3's fast Ethernet 0/0. So now when you look at the show interfaces status, it's a quick way to correlate where does that actually go. And then we'll also see this is how we can check the layer 2 VLAN assignment. Is the interface running as a trunk, or is it running as a layer 3 routed port, where it would say the keyword routed here as opposed to the number. Also says these are connected, which means the layer 1 status is fine. These other ones, these are not connected because the routers are in the shutdown state right now. But eventually the CDP timers should run. And now I know that my local fast Ethernet 0/1 is connecting to R1. And on their side, it's their fast Ethernet 0/0. Same with router 3, that my connection to router 3 is up. On their side, it's that port. Next change I'm going to make is to give these two routers layer 3 addresses. So router 1 needs an IP address, router 3 needs an IP address. At the interface level, I simply say IP address, the address, and the subnet mask. Doesn't really matter what it is as long as they're in the same subnet. Same on the link to router 3. IP address 10.0.0.3/24. In this case, I'm going to put both of the ports into VLAN 10, which means my first step is that I need to create the VLAN so that it's going to allocate a MAC address table that is specifically for that broadcast domain. Again, we can see this on the switch when we look at either the show VLAN or the show VLAN brief. One of the other results of this, by creating the number, what this is also going to do is allocate a spanning tree protocol instance. That by default, these switches run per VLAN spanning tree plus, which means that for each of these numbers, we have a separate instance of spanning tree, or a separate software copy or software process of spanning tree. We'll see a little bit later the reason why we would want that. But I have VLAN 10 created. The next step would then be to actually assign this on the interface level. There's a couple different ways you could do this on the switches. I could go to the ports individually and say, like on fast Ethernet 0/1, what is the switch port access VLAN assignment? In this case, would be VLAN 10. You could also use the interface range command, which is useful if you're assigning the VLAN on multiple interfaces at the same time or making changes on multiples of them, like interface range, fast Ethernet, interface range, fast Ethernet 0/1, comma, fast Ethernet 0/3. I could say switch port access VLAN 10. The other way is that I could define a macro that permanently assigns the interface range, which allows you to group the interfaces quickly together based on their role, like interface range web servers, interface range IP phones. So then you don't necessarily always have to keep track of what are the physical port assignments that go down to the devices. And the way that you would do this is to say define an interface range macro. I could say R1, R3, for example. And this is fast Ethernet 0/1, comma, fast Ethernet 0/3. Then when I go to address the interfaces, I could say the interface range is the macro R1, R3, and now it's both of them at the same time. So it essentially does the same thing. It's just kind of a nice shortcut to know that you can define these, which kind of helps to self-document the network. But regardless, however you get to the interface level, this is where the switchport access VLAN command is going to be. This is the number. There's also technically a way that you could assign this, which is controlled by a VLAN management policy server, or the VMPS protocol. In today's networks, this is kind of legacy, but you still can technically run it, where platforms like the Catalyst 6500 can be what's known as the VMPS server, which keeps a mapping table of the MAC addresses of your hosts. Then based on the layer 2 address, you can automatically assign them a VLAN. The problem is, though, you have to keep this huge table of all of the addresses in your network to what the VLAN assignments are. So in today's networks, there's a little bit easier solution for this, which is the 802.1x protocol. With today's implementations, you can actually assign the VLAN based on the authentication of the host. So when you open up your Windows machine, you type in your password, the AAA server or your Radius server can tell the switch what VLAN assignment to put it in. So we're not going to look at the example of this because we don't have a Radius server to talk to, but you could theoretically do it. If we look at the result of this now on switch 1, if we look at the show run, there's basically only one change that's happened at the interface level, which is the switchport access VLAN command. This now says that these two ports are going to be grouped together in the CAM table that is specific for VLAN 10. If I now wanted to see how is the traffic going to be switched between the two ports, I could look at this with the show MAC address table for VLAN 10. We'll see that the switch has a bunch of reserved MAC addresses that it automatically uses. These are for different control plane protocols. We don't really care what these are for right now. But you'll always see that the all Fs address is part of the MAC address table, because this is for what? That's the broadcast address. What we mainly care about are what are the MAC addresses that were learned. Where on port fast Ethernet 0/1, that's the MAC address of router 1. On port fast Ethernet 0/3, that should be the MAC address of router 3. If we were to take these two values, this one here and this one here, and correlate this on the routers with the show interface output, we should see that this matches what their burned-in address is. This is the MAC address that Cisco assigned to this interface driver when it created the router's card. So this here, if we were to look at the switch again, this should be router 1's value, which it is, BBBD3BC0. If we were to do the same thing on router 3 to look at the show interfaces, we should know what its MAC address is. So now the switch essentially says that for any packets that are going to this address, these are going to be forwarded out port fast Ethernet 0/3. Any packets that go to the address 0011 BBBD3BC0, that's going to go out fast Ethernet 0/1. If we were to correlate this with the ARP cache of the routers and look at the show ARP, once the devices actually go to talk at layer 3, we should see that they're going to know the MAC addresses of everyone in their broadcast domain. So your end host would normally know the MAC addresses of the other hosts on the LAN plus its default gateway. And then based on the IP addressing, it's going to figure out, is the destination local to me or is it on some remote subnet? In which case I'm going to use the MAC address of the default gateway. We could also see the details of the conversation between them if we were to debug ARP. Depending on who sends the request and then the response, we can see the routers actually building the frame once we send IP traffic between them. So on router 3, if I were to ping 10.0.0.1, I should see that on the other side, I received an ARP request. The source layer 3 address was router 3's IP. The source layer 2 address was router 3's MAC address. The destination layer 3 address was me, but they didn't know what my MAC address was. So this is them asking, what's your MAC address to IP mapping? I reply back to them saying that my address, my layer 3 IP address, has this MAC address associated with it. It's going back to router 3's layer 3 address, and it's going back to router 3's layer 2 address. When the switch received this frame, the ARP request, what does it do with this one? This one is going to be flooded. Because the destination MAC address of this request is what? Is all Fs. The ARP reply is a unicast. Because now router 1 knows what is the MAC address of who sent me the request. It knows the MAC address of router 3. So this reply here, this is going to be unicast switched based on what switch 1 says is in the CAM table. And this is going to be the fundamental point of all layer 2 switching, that any traffic within the VLAN, we need to consult this table to figure out how we're going to send the packets. Question?
Do multicast MAC addresses populate the CAM table?
They do populate the CAM table. There's a separate command. You would say show MAC address table multicast. It'll show you the port that it's going to and what the multicast destination is.
But in all cases, it will flood all these packets. They will be flooded across all the ports.
It depends.
If you
It
don't
depends.
have the snooping enabled, right?
Then it'll be treated as a broadcast, right?
Okay.
So the key is that if the layer 2 switch is not multicast aware, multicasts are treated like broadcasts. They're flooded everywhere. These switches are multicast aware by default. They run a feature that is known as IGMP snooping,
Okay.
where IGMP snooping is enabled by default. So the switch figures out what groups are the host trying to join, and based on that, it populates the CAM table. So it uses kind of a reverse flooding technique where it figures out what it's trying to listen to, not where the traffic is coming from.
Does Cisco still use they used to have their own protocol?
It was CGMP, the Cisco Group Management Protocol, is not used anymore.
Okay.
Because this one here, this is now implemented in hardware. And it's in hardware, right. And it's a standardized feature. There's an RFC that defines this.
Okay.
So anyone that has a layer 2 switch nowadays pretty much runs IGMP snooping by default.
Hey Brian, in your example, when router 1 did an ARP request to router 3 to get its MAC address, why didn't router 3 get the source MAC address to begin with? Because in your example, it had to go and ask for it, the MAC address, after it had already replied. Why didn't it get the original MAC address?
So in this case, router 3 is the one who generated the packet. Okay, router 3 was trying to ping 1. The first thing it did, once it looked at the destination, is it looks in its routing table, and it tries to figure out where is this packet supposed to go. In this case, there's only one route, so it knows it's going to this interface. It says the interface is running Ethernet, so now I need to build the layer 2 frame. which means I need to know what the MAC address is. So internally, the next step it says, do I already know the address? Look at the ARP cache. Previously, it didn't have it. So it looked in here, it says, what's the MAC address of 10001? Since I didn't have an entry yet, I'm going to have to ask them. The first output we see in the debug here, it says it's creating an incomplete entry. This means I'm going to send the request. So I'm putting a temporary placeholder in the table saying I'm trying to figure out what's the MAC address of router 1. I ask router 1. Router 1 replies with its address. This now goes into the table, and now I can do the mapping between the two. But on the other side, when router 1 received 3's request, since 3 was already putting its own address in here, this automatically populates 1's table. So what actually happened was that 3 sent the ARP request, 1 sent the ARP reply, but now they both know each other's MAC addresses. And what this is known as here, the ARP reply, this is sometimes called a gratuitous ARP or an unsolicited ARP. It means that you're sending a reply without someone's request coming in. And when we get to security, there's a feature that we need to talk about that's related to this. That I can update your ARP cache by sending you a reply without having to do a request. Because the protocol works both ways. When you send me the request, I now know your address. So I don't have to request you again.
Like the one that's being used for XRP and for, that's where we use gratuitous ARP?
Yes, that's one of the reasons you would want to use it. Yeah, and we'll talk about that when we get to it. Question?
What's the default age limit in the table?
I want to say it's something like 3 hours. If you look at the show ARP, you can see how old the address is. We may be able to see this if we look at the show IP interface.
Is that adjustable?
It is adjustable. It doesn't show here. The command would be the ARP, IP ARP, no, probably at the interface level, ARP timeout. And let's try this. Let's try 3600. No, it's not that then. For stuff like this, if you're trying to figure out what the router's defaults are, the best thing to do is to correlate this with the command reference in the documentation. This is one of the things I forgot to mention. For a lot of these examples this week, we're going to be correlating it with the documentation to see when you're actually doing these configurations and you need help on it, the best resource is just to look at their examples. So when you go to Cisco's main website, under the support menu, click this, and then all the way at the bottom of the page, there's a link that says Configure. There's 2 ways that you can go from this page. One of them is technology documentation that'll tell you generic things about like LAN switching or IP routing. Then under products, if you were to go to iOS, this is where the specific product documentation is, like in this case, iOS version 12.4 mainline. From here, there's 2 places you would want to go. The configuration guides, and under reference guides, the command references. We're going to come back to these when we get to the technologies in more detail. Like this is where you would figure out how do you configure BGP or how do you configure OSPF. But the counterpart to the command reference, this just shows you what's the usage of the command, what are the different arguments, and what are the default values. Like in this case for IP, this would be, I want to say this would be under addressing commands, which was the ARP timeout. Let's see if it's in this first section. ARP timeout. Default is 4 hours, 14,000 seconds. So it'll show you what is the command's name, so what's the syntax for it, what are the different arguments it takes, this in seconds. It says if you had a value of 0, it means that entries are never cleared from the cache. Normally you wouldn't really want to do that, but you can. Then under the usage guides, it tells you why you would want to change this. Like, what does this command actually do? So if we look at our final configuration for this, it's pretty straightforward. We just need to make sure that the VLAN is created. Then at the switch port, we say switch port access VLAN. That's going to put the membership there, which behind the scenes, again, is going to do a couple important things for us. One thing is that it's going to create the CAM table. That we now have a MAC address table that is specific for VLAN 10. The other one is that it's going to create our spanning tree protocol instance. And spanning tree protocol is going to be needed to prevent loops in the layer 2 network. If you have multiple links between the switches, it makes sure that you don't end up in an infinite traffic flow back and forth over and over and over.